Welcome back. Today we will discuss the description of flows. We know that a fluid, like any solid, consists of a very large number of interacting molecules. So when we talk of the property of fluid, what does the property of fluid mean? Let's take an example, density. To define density, we take a small volume delta V, measured the mass of the matter contained within that volume, and the density is defined as rho is equal to delta M by delta V. What should be the size of delta V? Suppose we have delta V with dimensions approximately equal to the size of the body. The density of the matter around the body varies from point to point, from location to location. As you move this volume, the amount of matter contained within the volume would change. If the size of this volume is very large, this would smother the variations of the density over the flow field. So, if we decrease the length scale of this volume, then the density measured by this volume, that is the mass contained in the volume divided by the volume, would change with the size. The narrower that we go, the more we are going to see the density variation. After a certain limit, if we decrease the size further, the density defined as delta M by delta V would not change very much. There are a very large number of interacting molecules in any gas. The number of molecules in a volume of 1 micrometer cube is of the order of 3 into 10 to the power 9 for gases at ordinary temperatures and pressure. This is a very large number of molecules. And so, the density defined by this formula would be approximately constant when the size of this volume is less than about 1 micrometer in length. If we decrease the size further, it is possible that we go into the limit. The size is so small that the number of molecules within this volume varies significantly. At some instant, there may be 20 molecules. At some other instant, there may be 25 molecules. At some other instant, there may be 15 molecules. So that we have a microscopic uncertainty as to the density. The region or the size or the length scale of this volume, when the density does not change with the size appreciably, is the region that can be termed as a continuum. The continuum model is meaningful only when the two length scales are quite distinct. What two lengths? One, the length that smothers the variation, the length that is of the size of the body, and the other, the length which is of the size of the mean free path of the molecules, so that the number of molecules contained within the volume can change with time or can change appreciably with time. In that case, when the continuum model is meaningful, it is possible to select a measuring length which is large enough so that only an aggregate effect of the molecular interaction is reflected in the measurement. But at the same time, it is small enough so that the macroscopic variations are not smothered out. The smaller length scale is of the order of the mean distance between the molecules, and the larger scale is of the order of the linear dimension of the body about which or through which the flow takes place. When a continuum model is possible, we can define a particle of the fluid. A particle of the fluid in the continuum model is an aggregate of the molecules within a small volume, which is large enough so that only the aggregate effect of the molecular interaction is reflected in the measurement, but which, that is the measuring volume, at the same time is small enough so that the macroscopic variations are not smothered out. We are able to use a continuum model in most engineering situations, and when we use this, we do not need to worry about the individual molecules at all. The length scale used in the measurement and analysis is large enough to be interacting with a large number of molecules. It is then possible to talk of the fluid as a continuous distribution of matter, and any fluid property may be expressed as a function of x, the three-dimensional space location, and possibly of time t. So that any property eta can be written as function of x and t, where x is the location of that point. Thus, we talk of pressure field and the velocity field that specify the value of these properties as a function of space points and time. Velocity is a vector, so it's a vector field. Pressure is a scalar, so it's a pressure field. These, of course, are the values of the respective properties of the fluid particles located at those points at those times. To understand the two types of descriptions that we use in fluid mechanics, let us look at this model. Here there is a fluid in which there are two different temperatures. The fluid with the light yellow color has a lower temperature. The fluid with darker yellow color is at a higher temperature. We have two floating temperature probes, a red probe and a blue probe floating with the fluid. They move with the fluid. The fluid at the higher temperature, the darker colored one, is pushing the lighter color fluid to the right. There is an additional purple probe that is stationary and it records the temperature. So let us see how these three probes see the temperature variations with time. You would notice that the red probe is constantly measuring a constant temperature of the fluid with a lower temperature. The blue probe is constantly measuring the temperature of the hotter fluid, the darker yellow fluid. And there is no change of temperature recorded in either of the two probes. But the purple probe sitting in between, the temperature changes as the interface between the two fluids passes through that location. Let's look at it again. The yellow temperature, which is at lower, and now it shifts up to the temperature of the darker yellow fluid. The red and the blue probes measure the temperature of the fluid as it flows with the fluids, but the purple probe measures the temperature at a fixed location. We have two kinds of flow description, as I said. One is what is called a material description. Here the flow quantities are described for each individually identified fluid particles moving through the flow field of interest. We follow each fluid particle as it moves around and describe its location velocity, and other properties as it moves around. Properties are measured by the probes moving with the fluid. In the last example, the blue probe and the red probe were measuring the properties of material particles because they were moving with the fluid. So they were giving the temperature of the fluid particles in immediate contact with the probes, and the probe was moving with the fluid. So particles in contact with the probes were fixed. An example of this is if we follow the time history of each of the migratory birds. This is each bird goes from where to where at what time, at what velocities are they flying. This would be the material description. When you study the motion of solid particles in solid mechanics, what you are usually doing is the material description. You follow each particle and worry about their location, their velocity, and acceleration with time. This material description is also known as a system approach, or the Lagrangian approach, or the material approach. These are equivalent names given by different writers. In this flow, we are following each particle as it moves around. If we write the location x, the velocity v, in any other property, say pressure or density, as a function of x naught, the location of the particle at time t is equal to 0. This location x naught, that is the location of the particle at time t is equal to 0, is used here as a label of the particle. So each particle has the same value x naught at all times, it's a label, and different particles have different values of x naughts. Their location at time t is equal to 0. So the location x at any given time is a function of the original location at time t is equal to 0 and the current time t. This map shows the movement of cyclone Nisarga in June 2020 on the west coast of India. It marks the location of the core of the cyclone on different times as it moves. This is largely a material description because the core of a cyclone consists of the same matter. This is a little more complicated picture showing the tropical cyclones in Australia over a matter of a year. You see, describing this is getting to be too complicated. And so we like to use a different description of the material properties in most cases. Luckily, we can do without it quite often. In this picture, we are showing a jet of water cutting a metal plate. If we are going to analyze this, we need to figure out the forces that the jet applies on the metal plate. It's a fixed location. We don't worry about each individual particle of water. We don't worry about what's happening to the particle over time. What we are worried about is what is the force that this jet applies at a location on the solid boundary, the solid plate where this jet cuts the plate. So, not only is a material description quite complicated, but we quite often don't need it. And therefore, we use an alternate approach, what we call a field approach. Here the fluid properties are specified as functions of space points and time. So V is a function of x, the space point and time. It is the velocity of whatever particle is at that location at that time. We don't follow the particle. So at a time t plus delta t, this function would be specifying the velocity of the particle which is at the location x, and which most probably would be a different particle than the particle which was there at time t. Similarly, eta, where eta could be any other property, pressure, temperature, density, stresses. These properties are measured by probes at fixed location, because we are expressing that as a function of space location x. This is also known as the Eulerian approach after the scientist Euler. If the velocity at a point in the flow field is increasing with time as shown, velocity versus time, is the flow accelerating? Most probably. If the velocity at a location is fixed with time, constant with time, is the flow accelerating? It could be. It is not necessary that the fluid has a constant velocity. The fluid may still be accelerating even though the velocity at a given location is constant with time. This needs further explanation. Consider a converging channel in which a fluid is flowing like this. At the left end, the area of the channel is larger than it is at the right end, and it is possible to have a flow where the mass flowing through the channel does not vary with time, and in that case the velocity at the left end would be lower than the velocity at the right end, because the same mass now flows through a smaller area. If I plot the velocity versus location x, then we get a curve like this. The velocity is increasing downstream. Now, I fix a probe at the location x1, and if I measure the velocity at location x1 with time, then I get a constant velocity independent of time. It does not change. But if I fix the probe at a location x2, the velocity there is constant with time too, but this velocity is larger than the velocity at location x1 at all times. If a particle starts at location x and starts moving, then its velocity would increase. See the picture on the left. As the particle moves, it experiences an acceleration. So though the field of velocity V is function only of x, not of time t. Each particle in the flow is undergoing an acceleration as it moves down the channel. We need to worry about this, because if the particle is experiencing acceleration, then there must be a force on that particle which causes an acceleration. Newton's law of motion. So, if we see the velocity at a given velocity at a location is not changing with time, it does not mean the fluid is not accelerating. Let's now discuss the time rates of change experienced in fluid mechanics. For this, we have created this image where we have a row of particles of different size. Suppose the size of the particle is expressed as a variable eta, del eta by del x, which is positive, constant. It is the value of eta, the size, is changing to the right. Now suppose all these particles are moving with the velocity v. After time delta t, the original row is now located at this configuration. The blue arrow is an observer observing the fluid property. If the blue observer has closed its eyes at the start of the motion and opens its eyes delta t time later, then it will see this picture. It will record that the size of the particle, the property eta, has decreased. What has happened? What has happened is this. Now, a particle which was v delta t distance behind the original particle at the diamond probe has occupied this location. The whole row has moved a distance v delta t to the right. So, if the size of the particle was not changing, then originally it recorded particle which was at this location x, but delta t times later it was recording the size of the particle which originally was at minus v delta t behind the current location. So, change in property observed is delta eta is equal to del eta by del x into minus v delta t. This change has been recorded purely because of the motion of the particle. So, this change can be called the convective change following the lead from heat transfer, where the convective heat transfer is because of the motion of the fluid. So, this change in property eta is solely because of the motion of the fluid particles, and of course because of the gradient of the property eta in space. Because if delta eta by delta x was 0, then all particles were the same size. No motion would show any change in the value eta at the location of the probe. Now, if in addition during this time delta t, the size of each particle increases, if the size of each particle increases, then the change in eta observed by this observer would be the original convective change delta eta by delta x into minus v delta t plus the rate at which the size of the particle grows. And we denote it by capital D eta by delta capital dt. Capital D eta by capital dt is the material rate of change of eta with time of the actual particle, the growth of the size of each particle. We call this the material rate of change. And so the total change in time delta t would be capital D eta by capital dt times delta t. So the total change observed by this observer would be the convective change plus this material change. And the rate of change with time is given by the equation at the bottom of the slide. Delta eta by delta t is equal to minus v delta eta by delta x plus d eta by delta t. Del eta by del t on the left is the observed rate of change. We call it the local rate of change. Locally observed rate of change by a stationary observer. A field description, an Eulerian description. And this consists of two changes. One is the rate of change minus v delta eta by delta x, which is the convective rate of change, plus capital D eta by capital dt, which is the material rate of change. The local rate of change is made up of two things: a convective rate of change and a material rate of change. So repeat, the local rate of change d eta by dt is made up of two changes. One, convective rate of change, and the other, the material rate of change. This equation is conventionally expressed in this form. D eta by dt, the material rate of change, is equal to the local rate of change plus the convective rate of change. This cartoon explains this quite clearly. There are two scientists, Mr. Euler, who is stationary, and he reports a local rate of change at 2 degrees per hour, rising at 2 degrees per hour temperature. Mr. Lagrange, of the material property fame, is floating down the river on a boat, so he's measuring the material rate of change, and he says the temperature is dropping at 1 degree per hour. What's happening? That there is a spatial gradient. There's a convective rate of change that defines this difference. Let's take an example. On a given day, temperature at Dehradun is 15 degrees Celsius at sunrise, and at the same time, the temperature at Jhansi, almost exactly south of Dehradun, is 25 degrees centigrade. Jhansi is about 500 kilometers from Dehradun. There is a 30 kilometer per hour wind that blows due south, and the air heats up at the rate of 1 degree Celsius per hour. What is the rate of rise of temperature at Jhansi? To understand this, let us understand what does air heats up at 1 degree Celsius per hour mean. Is this the local rate of change or the material rate of change? It clearly is the material rate of change. Each individual particle of air is heating up at the rate of 1 degree Celsius per hour. There is a spatial gradient of temperature. Temperature rises from 15 degrees Celsius to 25 degrees Celsius over a distance of 500 kilometers. So del T by delta X is 25 minus 15, that is 10 degrees Celsius divided by 500 kilometers. The local rate of change at Jhansi, del T by del T, is dt by dt minus V dot delta T by delta X. Material rate plus the convective rate. V dot dt by delta X is equal to 30, velocity is 30 kilometers per hour into 10 by 500 degrees Celsius per hour. So the local rate of change is 1 minus 0.6 or 0.4 degrees Celsius per hour. So even though each particle of air is heating up at the rate of 1 degree Celsius per hour, the local rate of change felt by the resident of Jhansi is only 0.4 degrees Celsius per hour, because the cooler air is moving in from Dehradun. This is from the property eta that we wrote, this relation. For vector form, we can write this equation as delta eta by delta d eta by dt is equal to delta eta by delta t plus vector v dot, the scalar dot product, time gradient of eta. If eta is taken as the velocity, then dv, d velocity by dt, is acceleration. dv by dt is del v by del t plus v dot del v. This is known as Euler acceleration formula. The term on the left gives you the actual acceleration of a particle. This is a material description, a Lagrange description. The first term on the right is the local rate of change of velocity, and v dot del v is the convective rate of change of velocity or the convective acceleration. The material acceleration is local acceleration plus the convective acceleration. Those familiar with simple vector operations would recognize that v dot del v consists of three components, I, j and k in the 3 direction. In the I direction, the component is Vx, delta Vx by delta x, plus Vy, delta Vx by delta y, plus Vz, delta Vz by delta z. Similarly, in the y direction and the z direction. We do a simple example. Let the velocity field be a into x minus yj. The velocity component in the I direction, the x direction is ax, and in the y direction is minus ay. If we plot this velocity at a few points, we get a picture like this. Along the x-axis, where y is equal to 0, the velocity is axi. So velocity is horizontal and it is increasing as x increases. Along the y direction, where x is 0, the velocity is minus ay. So velocity decreases toward the origin and is directed towards the origin. At other location, the velocity vectors are as shown. Now let's determine the acceleration. Acceleration of particles which are at location x and y. Ax, the component by the Euler acceleration formula, was Ax, the x component acceleration is delta Vx by delta t, the local rate of change, plus the convective rate of change. And if I evaluate each of this term, I get Ax as a square x. There is no Vz component. There is no component normal to the plane of paper. Ax is this. Similarly, Ay is evaluated by differentiating this with respect to t, x and y, and we get a square y. So the acceleration vector is a square xi plus yj. This is the acceleration of the particle which would be at that in the location xy at a given time t. Note that the acceleration is independent of time. The velocity was independent of time, so acceleration is also independent of time. If the velocity is independent of time, why is there an acceleration? Because acceleration is only rate of change of velocity. No, this is velocity field. This is Eulerian description. So even if the velocity at a given point does not change with time, the particle at that point may be undergoing acceleration, because when it moves to the next point where the velocity is higher, that means it has undergone an acceleration. And if I plot this acceleration field, the acceleration field looks like this. These are the acceleration vectors at all times. Let's go to classification of flow fields. We have a one-dimensional flow field we call when the velocity description Vx is a function of only one space variable. In this channel made of two plates, one of the plates may be moving, there is only x component of velocity Vx, which is a function of y only, so it's called a one-dimensional velocity, one-dimensional field. Similarly, flow through a pipe. We have seen before that flow through a pipe at laminar regime has a velocity field which is parabolic, and it is a function only of r. Vz along the axis is a function of r. This is one-dimensional. If the channel was slowly tapering, very slowly tapering, the field is no longer one-dimensional, but the variations with x direction are slow, and so it can be treated as a quasi one-dimensional. Similarly, we have a name, steady flow. Steady flow is that flow field where the properties do not change with time. So at location x1, the velocity is constant with the time, and well, at any other location x2, the velocity is constant at the higher value for all times. This flow is termed steady flow. So in steady flow, the local gradient is 0. If we are using the property velocity, then del V by del T is 0. The local time rate of change of velocity is 0. But it does not mean that the acceleration is 0, as has been established earlier. In this flow from a large reservoir through a small bored tube of long length, the level of the fluid in the reservoir would change very slowly, so that the velocity of the flow or the flow rate through the tube of area A is going to vary very slowly. And so at a given time, this can be treated as a steady flow. Such flows where the variations are very slow are called quasi-steady flow. We would have occasion later to amplify this assumption. A uniform flow is a flow in which the properties are constant at all x's and y's. That is, everywhere, all properties have the same value. In some cases, we can convert an unsteady flow to a steady flow simply by change of frame. There is a body that is moving towards the left with a constant velocity. Let's consider a point A at a location x naught, y naught and record the change in velocity. Originally, the velocity there would be 0, but as the body moves towards A, the velocity increases, and as the body moves past A, the velocity decreases back to 0 again. So the velocity at A would appear something like this. In this video, which is a famous video from 1933, recorded by the great German aerodynamicist Ludwig Prandtl, we show a body moving in a fluid and the flow is unsteady. We can make this flow steady by changing the frame of reference. Now we attach the frame to the body. Here, the point B is in the frame x naught prime, y naught prime. The body is stationary in this frame. The fluid moves past this from left to right as the velocity v. Then the velocity at point B would always be same, invariant with time. The value would be depending upon the location of B relative to the body. If it is closer to the body, if it is at the nose of the body, the fluid at the nose is always at rest. But far away, the velocity is equal to v, the speed of the body. This is shown in this video again by Ludwig Prandtl. The flow is now steady. Thank you very much.